Okay, so I'm just gonna like work a ton of problems because I feel like in my other videos I've previewed most of what this is talking about. So this is some chapter 6, yeah. Did you know the sum of the forces equals mass times acceleration in that distance, direction? Awesome. Okay, whoa, what just happened? Some kind of science. Okay, Meops. So let's look at this problem. So we have a traffic light of a mass suspended, and we want to find the mass tension in each wire. Okay, I think I warned you about this problem. So I have let me draw this picture, I guess. I have cha-chonk. I guess that was supposed to be 30, so I'll make it a little narrower. And then ka-chonk, and then there's something here. I'm going to do this, even though it's not in the picture, just to kind of mess with you on purpose. And then this is 30, and this is 45, and then this was, I already forgot, 15 kilograms. Okay, now, I'm going to do something that's really important, because what I could do is, there's a couple of things going on here. So, there's this wire, and there's this wire. And there's this wire, and there's a box. So, in theory, I could draw a free body diagram of this knot like this, but chonk, 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 chonk. And then I could draw a free body diagram of the box here, and the box would go ka-chonk, ka-chonk. Now, because this is the same wire, and internal forces are equal and opposite, if I put this together, those two forces go away. And it's not asking for the tension in the cable, not even that it's really in this picture. It's not asking for the tension in the cable that suspends the light. Okay, this seems like I'm going way off base for no reason. But this is the kind of thing that if you're a certain kind of student, you're going to get hung up on and not be able to get over. Because you're like, well, technically there's something in between the knot and the light and we're ignoring it. We're actually not ignoring it. The knot and the light are, what's the word? I was going to say static with respect to each other. Yeah, I mean, they're not moving with respect to each other. Therefore, we can treat them as a giant blob. So if I go like this, whatever value I get for here, like if this turns out to be 12, this is going to be 12. So this would be minus 12 plus 12. So then whenever I put the whole thing together, the minus 12 and the plus 12 cancel out, and I still end up with only these external 1, 2, 3 forces here. So I'm going to take a leap and pretend that you understood what I just said, and if you didn't, that's okay, and if you hadn't even thought about that yet, that's okay too. But what I'm going to do is something that I feel like I would have been really offended by as an undergrad and been like, but you can't do that because clearly there's geometry in a cable and it's not a dot. I'm going to pretend that the entire system here is just big giant blob. Okay, so we have big giant blob being held up by two cables. Okay, and since I don't care about the shape of big giant blob, I do know how much the blob weighs. Blob weighs 15 kilograms. I can just do this. Point. And now it's quote unquote, look how much easier it is now. But it's simpler, and again, you're like, well, it could be swinging in the wind. Yeah, okay, but we're not doing that yet. Right now, we're just trying to do the basics of what is the tensions in the cables. So I just wanted you to kind of understand why we can make those assumptions. And if you were never going to, you're like, I wasn't going to question it anyway, then don't worry about it. But basically the idea is that we can now say, okay, there's going to be, since there's a knot holding this on, it's not the same, it's suspended from two wires, so they have two different tensions. So there's a tension and a tension, and then the box itself has a weight. So we have a weight, a tension 1, and a tension 2. Okay, That's the free body diagram. If you can't get this picture right, you can't do the rest of it, so there's really no point in keeping on with this problem. Okay? So, now the first thing that I'm going to do is I'm going to break these up into pieces. So, I'm going to go tonk, tonk. So this is the adjacent side, so t cosine 30. This is the opposite side, t sine 30. And this is, again, why I'm not memorizing x's and y's. This is the opposite side. Oh, this is t1, t1. That looks like a 2. That's going to get me in trouble. Okay, t2 cosine 45 and t2 sine 45. Okay, and then I can pretend these don't exist anymore. If you want to redraw your free body diagram, you can, but I get confused when I do that, so I'm not going to. I feel better just looking at it like this. Okay. Now, the sum of the forces in the x directions. Okay. I have negative t1 cosine 30 degrees. And I'm putting negative because this arrow is in the negative direction. All right. Then I have, it seems like an unnecessarily thick pen. Oh well. I'm committed now. And then I have t2 cosine 45 degrees, and that equals mass times acceleration in the x direction. Now, I happen to know, well, I guess I don't happen to know. Does it tell me? Well, it doesn't tell me. I'm assuming that this isn't moving. So it's a non-moving traffic light. It's a hanging out traffic light. So 0. Okay? So now I can say, okay, well, t2 cosine 45 degrees equals t1 cosine 30 degrees. If you want to do it that way, or you can just leave it as being equal to 0. How am I going to do it? You know what? I'm going to do it, leave it the way it was, because I'm assuming you know how to solve two equations and two unknowns the regular way. I'm going to make sure you can solve it with matrices. All right, so I have negative cosine 30 degrees t1 plus cosine 45 degrees t2 equals 0. Okay, now I have the sum of the forces in the y direction. Okay, so I've got t1 going up with a sine 30. I have t2 going up with a sine 45. I have w going down, and that equals mass times acceleration in the y direction. And again, acceleration in the y direction is 0, because it's not moving. Okay, so that's sine, and there's a reason I'm doing it in this order. Sine 30 t1 plus sine 45 degrees t2 equals the weight. Okay. And I know the weight is 15 times 9.81. Okay, 15 times 9.81, 147. So I'm going to go 147. Okay. So although I can solve two equations and two unknowns without any problem, generally I want to make sure that you guys know how to do this with matrices. You may or may not remember that you can set things up where you pull the coefficients from these. I'm only going to do this once, but see how, let me take this one here, and I have this here. Okay. Do you see how I've got, okay. Do you see how in this problem I've got the t1s lined up and the t2s lined up, and everything that doesn't have a variable is on the other side? So I have two equations, two unknowns. So what I can do is I can take the coefficients here, and I can basically plug them into a matrix. So I'm going to go make a matrix, negative cosine 30, cosine 45, 0, sine 30, sine 45, 147. I'm going to use this amazing calculator button called reduced row echelon form. Reduced row echelon form. And somebody tried to teach this to you at some point. You're like, this is stupid. I'm never going to need it again. And that's fine. And this is what it looks like on my 89. And you can do it on your calculator, however you want. Am I in degrees? Yes. Cosine 30. Oops. Comma. Cosine 45. Comma. 0. New line is a semicolon. Where's my semicolon? Semicolon. Blah! There. And then sine 30 and sine 45 and 147 and end my bracket thingy. Okay, so cosine 30, cosine 45, 0, sine 30, sine 45, 147. Now, I'm going to go into my math thingy and under matrix, RREF, number 4. So I'm going to RREF that thing. Okay, and see how on the left it goes 1, 0, 0, 1? So basically that correlates to the first thing that you wanted is 107 and the second thing you wanted is 131. Okay, so the first thing I wanted, because I had them in order, like my first thing was T1 and my second thing was T2. So the first thing I wanted was 107, we'll call that 108. And the second thing I wanted was something else, 132. And I'm in newtons. So look, I just did all this without having to remember how to do algebra. 108, I mean, I did linear algebra. 108, 132, are those answers even remotely close to what they did? Wow, it took them a while. Yes, yay! Okay, so I strongly recommend you remember how to do this because we're going to have lots of these kinds of things to do. But it all comes down to, if you don't have the free body diagram right, it's over. And then it gets tricky because it's like remembering, oh, this one's a negative sign, and then this is, and I think also as a student, I would get confused about, does this W go here or here? And you have to remember, this W is with the free body diagram. So you just draw the free body diagram. Everything on the left side of this is from the free body diagram. These are all forces. And then everything on the other side, this is mass times acceleration. Okay, so if you're really consistent with how you always set up your equations, then it shouldn't be too terribly awful. And I think I'm going to just do one example per video so you can just watch which ones you want. Yay!